tutorial series on deep learning, and today we shall be looking at the backpropagation and how we can actually use the computational graph to be able to do our backpropagation. And so in the previous series, we've looked at neural networks, and we talk about how you can build your computational graphs in which each of the nodes actually holds a data or holds a computation. When I say computation, I'm talking about whether it is plus or times or you have a function. Okay, so backpropagation. And remember, this is a typical example we're trying to use. This is our x, that our x consists of 3 variables, and we're trying to we decided to use three neurons as our hidden layer, and we have just one neuron in our output layer. Don't forget something very important I always say. I always see this activation as a replacement to this input. This activation as a replacement to this. This activation as a replacement to this. I find it easy to understand that. So these activations will now become the new input to this neuron. So as you can see here, you see that after calculating these activations here, it now becomes our new x. It becomes our new x, as you can see. It becomes the new x to the new weight matrices. In other words, essentially what the activations are doing is the activation are encapsulating the features of the x's. That's why when we get to computer vision, we say it's a feature representation. That is, it has in itself is carrying the properties of the features. It's carrying the properties of the feature. Even when you go to natural language processing, and we talk about word embeddings, and you see that particular node is able to carry the meaning of that particular word in the sentence. Okay, so we gone through this, and we also showed us this how this computation is derived one after the other. That it's easier to build a graph with this computation, and these are the nodes that carries the computations that are being done, while the edges are actually carrying the data. Now, so let's see how we do a backpropagation. Not to lose sight of the reason why we're doing a backpropagation, we essentially said that we do a forward propagation for us to be able to do our weight matrices multiplications until we get and we squash through our activation functions, and we actually get our prediction. Now after we've gotten our predictions, we take our predictions and go into our data and go check the target labels for each of our data instance and compare our prediction with the target label. And we do some error analysis to be able to see how far away is our prediction from the actual label. And once we have done that, we sum it up for all the data instances, and for us to be able to readjust the weight matrices, which are essentially the numbers that are affecting how much importance each of the features are. Then for us to do that, we discover that we need to do a differential equation of the total error based on the number of weight matrices, that the number of weights that we have. So now, for instance, in this case, let's see a simple example of backpropagation. Here, what we have here is we're having a function that takes in 3 inputs, x, y, z. So these are our input, x, y, z. And that function, what does it do? It adds x with y and multiply the result with z. In order for us to model this function, we draw it this way. X, y, z becomes our input. We have a plus, which is our computation. So x and y are the two that are involved in the computation, and we get a result. In the result of our x and y, the addition of our x and y, we can store it in a temporary variable called q, and we'll multiply that result with z directly. And once you add this, a computation that holds a node that holds the computation multiplication, once we multiply our q with z, then we have our f, which is what our function is producing. So if you now want to replace these variables with values, let's say our x is -2, our y is 5, and our z is minus 4. So for us to be able to do the computation, minus 2 plus 5, we get a 3. Then 3 times minus 4, we get a minus 12. Now for us to be able to do a back propagation in this place, so the back propagation we're trying to do is we're doing a differential equation. We're differentiating the final output, which is L, with each of the input variables x, y, z. So how does that work? What we actually want is this. We want the partial derivative of f with x, partial derivative of f with y, partial derivative of f with z. And for us to be able, this is what we need to get. For us to be able to do that, in order to do that, okay, we say that we have an intermediary variable, which is q. So we can actually do the partial derivative of q with x, partial derivative of q with y. Then we can do partial derivative of f with q, because it's directly connected to it, and partial derivative of f with z, because it's directly connected to it. Then by so doing, we know that our f is actually our q multiplied by our z. So let's see, how do we do a partial derivative of q with x? To be able to do a partial derivative of q with x, the representation of our q is x plus y. So in doing a partial derivative of q with respect to x, we just differentiate this one with respect to x, it gives us a 1, and this is gone. And when we do the same thing with respect to y, when you do a partial derivative of this with respect to y, this one is gone, this one just gives us 1. I'm sure we remember how to do derivative. When we have y is like 1, and so this is going to give us 1 times y raised to the power 1 minus 1. That is derivative when we're differentiating with respect to y. Okay, so now when we're trying to do a differentiate f with respect to q, it just gives us z. When we differentiate q with differentiate f with respect to z, it just gives us q. These are just standard mathematical differentiation, which you can look up in calculus resource or text materials. Okay, so when we're starting from this place, if you're differentiating partially differentiating f with respect to f, it just give us 1, and you do the partial derivative of f with respect to z, and we have already gotten it here. That gives us q. So what is our value of q? X plus y. So it just become, what x is minus 2, y is 5, and that gives us 3. Then we do the partial derivative of f with respect to q. F with respect to give us z, and what is the value of z? Z gives us minus 4. Partial derivative of f with respect to y. What is the partial derivative of f with respect to y? You can see in this case, to do the partial derivative of f with respect to y, we can use the chain rule, because we don't have the value of partial derivative of f with respect to y directly, but we have f with respect to q, and we have q with respect to y. So we can go through q to be able to get the partial derivative of f with respect to y, and that is the partial derivative of f with respect to y. We beat the f, the q, then we just put the q, the y. So this can cancel this and give us the f, the y back. Okay, so this is what we call the local stream, because this is the local stream, and this is what we call the upstream. And this is coming from the output, from the back propagation. That's coming from our output. Now to do the partial derivative of f with respect to y, we get our df dq. By the time we do our df dq, it gives us z, and our z is equals to minus 4, and our dq dy give us 1. By the time we multiply 1 by minus 4, we get this minus 4. Partial derivative of f with respect to x follow the same thing, and by the time we do that, we get minus 4. Now we now have this minus 4 has replaced minus 2. This minus 4 has replaced 5. This 3 has replaced minus 4. Remember in previous series, we mentioned that we arbitrarily start the value of our input x, y, z with arbitrary values. In this case, we started with minus 2, 5, and minus 4. But after doing backpropagation, we have adjusted the values to minus 4, and 3. So that is essentially what the backpropagation is doing. We are having the upstream, which now we differentiate our total loss with respect to z, and we differentiate our z with respect to x, and we can use the chain rule to get all our values. In another example, as you can see here, in this case we have what we call the ReLU function, or something that is close to ReLU, a maximum function. So here, this is our function. It takes in x plus x, y, z. It adds x to y, and the result is multiplied with the max of y and z. So let's say we now initialize our variables with x equals to 1, y equals to 2, and z equals to 0. So what you can do is to build a computation graph. To transform this into a computation graph, it looks like this. X and y, we do a plus, and y and z, we do a max. Then the result, we do a multiplication. So we can say the plus, we can assign that to a as an intermediary variables, and the max, we can assign that to a b as an intermediary variables. Then our final value will be f, which will be a multiplied by b. So now putting in the numbers, by the time we do our forward propagation, our x is 1, our y is 2, we do a plus, we have 3, our y is z, our y is 2, z is 0, we do a max, we get a 2, we do a multiplication, we get a 6, then our f gives us a 6. Now, by the time we now want to do our partial derivative, we know that we are differentiating our final value of f with respect to all the variables. But we can't get all the input variables directly, then we have to go through the intermediary variables. So to be able to do the partial derivative of a with respect to x, so this is our a, we do partial derivative of a with respect to x. So by the time we go through this function, do a partial derivative of a with respect to x, we knock off this, gives us 1. It will be a partial derivative of a with respect to y, we knock off x, it gives us 1. Then here, we do a partial derivative of b with respect to y. And then we do a partial derivative of b with respect to y, it gives us 1. And do a partial derivative of b with respect to z, and that gives us 0. This is a little bit tricky, and let's look at it. Now, we're doing a partial derivative of b with respect to y. Now, we say this one gives us a 1. Well, it gives us a 1 if y is greater than z. Now, what is y? Y is 2. What is z? Z is 0. And 2 is greater than 0. So this gives us a 1. This is just an intrinsic mathematical operation of the max. We do a partial derivative of b with respect to z. This also gives us a 1 if z is greater than y. Now, because y is our base here, is our variable of interest. But because z is 0 and y is equals to 2, it doesn't give us a 1, it gives us a 0. So the final value here is actually 0. So we've gotten all those intermediary derivatives. Then we can do the partial derivative of f with respect to a. This will give us a b. Differentiate partial derivative of f with respect to b. This will give us a a. And the value of our a and b are 3 and 2 respectively. So at the end, we get into our upstream, which is our f. So we do the partial derivative of f with f, which is 1. That's our upstream. We're going to multiply, so this gives us a 1. Then we go on to our local stream, which is now we do a partial derivative of f with respect to a in this place. And by the time we do partial derivative of f with respect to a, give us 2, which is the 2 here. Partial derivative of f with respect to b, it gives us 3, gives us a, which is the 3 here. And by the time we come in here, we have the partial derivative of our b with respect to y. Partial derivative of b with respect to y, it gives us a 1. Okay, so that gives us a 1, and we now multiply the 1. This one gives us a 1. We multiply the 1 with the upstream, which is 3 times 1. So this is updated to 3. Here we do a partial derivative of our b with respect to z. That gives us a 0, and we do it multiplied by the upstream. The upstream value is 3. This gives us a 0. The same thing goes here. We do a partial derivative of our a with respect to x, gives us a 1. We multiply by the upstream, which is 2, gives us a 2. Partial derivative of a with respect to y, it gives us a 1. We multiply by the upstream, which is 2. So essentially, this is what we're trying to calculate. To be able to get our value, which is the downstream, we multiply the local stream, that's our derivatives that we're getting here, multiply by the upstream, that is what is being carried from the backpropagation, from earlier values in the backpropagation. At the end of the day, here we have 2 here for y and 3 here for y. So because y has 2 edges, then we sum up just like we're having 2 pipes that links into a particular bowl. So y gets accumulated and it gets a 5. Z is 0 and x is 2. So 2 replaces 1 for the value of x, and 5 replaces 2 for the value of y. 0 replaces just 0. That means z does not change, so z is still 0. So these values here, 1, 2, 0, just to reiterate, are the values that we keep updating. These are our weights that we keep updating, keep changing, that we keep learning a weight that actually gives us the best at the local minimum. So in this case now, we have updated our weight matrices from 1, 2, 0 to 2, 5, 0. And we continue like this for a certain number of iterations until the changes remain constant. Then when that happens, we say that our algorithm has converged. That is, the backpropagation is converged. One thing that we notice in this place is this. While trying to do our backpropagation, there are certain things that we noticed, and that is where we're going to continue from in the next series. Thank you for listening, and do let us know what your comments are.